Yes, introduction to convolutional neural networks. I know that a lot of people knows this. Some have some details and some have no knowledge. So I hope to help you a little bit here. I will cover what this is, because this is the main thing we are doing in visual intelligence. I mean, convolutional network is the backbone of a lot of networks and research we do. I will also talk a little bit how to train these networks, and finally why they fail. So it's a little bit for everyone. Yeah, we start with features. If you're analyzing data, features is what you are aiming to design. That's a data representation, a data description, something that will help you. If you have this feature, you can gain inference. You can use them to gain some inference of the task you want to solve. And that is, capturing these features is what really matters. And also for images, there is applies. In the early days, we had lots of features have been invented, and that was pattern recognition scientists was doing, was inventing features in the old days. If you look at, let's say, a leaf, you're gonna look some shape features. You can reduce the whole image to some few coefficients that you estimate, which will help you. Then we have these key point features, like in the middle here, you find some key points in the image and you make some inference and you do some clustering of them. And finally, something called histogram of oriented gradients, which was more or less the standard thing or state of the art before this deep learning came into place. The challenge is that making these features in images is extremely difficult. The first thing is you want to separate bananas from orange. That's a simple thing. You have color and you have a shape. That's a fairly easy thing to do. But how can you describe the content of the images below? We all see this as a dog. But how can you tell that computer that this is a dog? You can tell, you can have some idea that have 2 eyes and 4 legs and all these things. But now you see half of the head, and we still see this is a dog. And telling the computer that this is a dog or making it to understand that's very hard. The other 2 complex scenes, you can, let's say the first one, you're in a park, yeah, you look for green. But then the boat there is green. Is that a park? So how can you tell it? So this is hard. And yeah, and that was the thing. Before 10 years ago, this is what we tried to do, figure out the good descriptors to describe these things. And we have these architectures for image recognition system. That was first one, yeah, you had this, try to invent some good features, you feed that into some kind of classifier to figure out what's the content of the image. And then it started to be more advanced. So you did some kind of feature extract, let's say the key points, and then you did some more advanced in clustering or some Fisher vectors that we call all these things, and you fed that into a classifier and a little bit better. That was 2011. And now we are working with deep learning, and you have this hierarchy of feature extraction from low level, meaning at the pixel level, and up to mid level, high level, and then trainable. And the question what we want to solve is how can we make all the modules trainable and get them to learn the appropriate features simultaneously that we learn the classifier. And this is what we use these deep neural networks to. So we don't invent the features anymore. We make a network that figures them out automatically. Okay, so the talk will be about how can we design this network to do that. In order to do so, we have data. Data is essential in every machine learning system. We have training data, which we know labels or objects used to train the algorithm. Validation data, which we measure the performance of the algorithm during the training. And then finally, we have some test data that we can use to assess, okay, this is the overall error rate after that we are done. So this is, I'm going to talk much about, but these are in behind everything we do. So data is essential. And a lot of work we do here is in visual intelligence is to get rid of these labels, reduce the amount needed for them. Okay, moving back to neural networks. The building block is the McCulloch-Pitts mathematical neuron, which is quite simple, very simple actually. It is input data that is called X here, you have here at the input, and you multiply them with some weights, and you do summation, and you send them to a nonlinear function, and that's the output. And the aim here, what we want to do is to figure out what should these weights be. This is just one neuron. And we are lucky for and they have an inspiration is from the human brain. I will not talk much about that because I know nothing about the human brain. But that's the inspiration. And like in the brain, you connect them to a network. So the input of one neuron is now the output of one neuron is input to the next, and so on. And we have a lot of these mathematical functions for each of the neurons here propagating through the network. So you're sending signal in here, you have weights here, you send it through, you do summation and a nonlinearity function, that goes through all the neurons in the next layer, or some, you could decide, of course. And all these things go on and on and on. So there's a lot of mathematical operations to do. And you have a lot of weights you need to figure out what they should be. So the question was to ask is, why a nonlinear activation function? Well, there are some reasons for that. The first one is that is to introduce nonlinearity into the network. So that, because response could be very complicated of what you try to do. It also allows the model to, so that means that it allows the model response to vary nonlinearly with the explanatory, the input data. And if you didn't do that, one neuron will be sufficient. You can just have one, and because it all will collapse to that one. It's just like linear operations. So that's the reason. So it will have a very limited modeling capability. But typical nonlinear activation functions is sigmoidal and ReLU. And leak ReLU are variants of this. It used to be sigmoidal in the 90s, and now everyone is using ReLU or some variants of that, or something that is better now. So that is the first part, and then we need to, okay, how can we figure out the weights? And that's normally we do an optimization problem. We have a mathematical loss function which measures the distance between the predicted variable that is output of this network and some desired, what we have is known as the ground truth, the training data coming from the training data. And we measure the distance. How far away are we? So if you do regression, maybe the minimum mean squared error distance will be fine. If you do classification, we often use something called cross entropy, which is the measure of how well are we doing. And we compare that, and we feed the feedback back to the network and adjust the weights. So in the next time we do a little bit better. Okay, we measure how good are we. Okay, we send the feedback back and we measure it and go on and on and on. And this takes a lot of compute. So that's why we are often using GPUs, graphic cards, in order to speed this up. How can we do this? How can we send this signal back? Well, for doing that, let's think of we have a loss function here. We have this J here. So we only have one network, a network with one variable. So it's a very, very simple one. It's not useful in any practical applications, but this is what we have. We can draw a loss function here, and let's say we initialize a weight here. Okay, if you are on that weight, we have the optimal weight because the loss function is the minimum. So this is where we want to be at the bottom. We start at 1 point, just a random pick, take one. And then we compute the gradient, taking the derivative. So you need the calculus that you learned back in high school. Okay, we compute the derivative, and then use like a Newton optimization algorithm, kind of, and in order to move in the opposite direction. So okay, we go in the opposite direction, weighted that by some factor call, and then we go back and we end it here. Okay, fine, a little bit closer to the optimal, and then we do it the next time, and we have a new derivative at that place, and so on until the derivative is more or less 0. And then we are done. So this is an important factor. It's called the learning rate. So when I talk about the learning rate, is how much emphasis you put on the gradient when you update the parameters. And if it is too high, it doesn't work. It explodes. It will be very noisy. And when it's too low, it doesn't move. It's moving so slow. Okay, this is just a single neuron. If you go into a network, we have a lot of these things here. And then let's say we want to update the parameter here. We need to propagate from the output, taking the derivatives all the way down to the one where I want to be here. And this is called backpropagation, because we are propagating from the output back to the place where we want to update the weights. And this is just a mathematical chain rule we learned in the early days of the universities. And so basically that's it. And for this network, I can compute it analytically because I know all my loss, I know all the activation functions I have. So this is can be done. And this is a nice thing. We do that, and a lot of compute. So we need to compute all these things here and in order to update the weights. Okay, so far so good. Now we want to move into images. And then we have a problem here, because you see here, I've connected my input data here to a lot of neurons in the next layer. So if I want to do that with images, let's say I want to have one image here, and I have a hidden layer with the same size as the next one. Then I should connect all my pixels, which could be, and this is a small image, just 200 by 200 pixels, to the next layer. That means I will have like 2 billion parameters to estimate just with the first layer. This is crazy. So what we do instead, we think, okay, most likely this spatial correlation in images, I mean, things that happen here is not that dependent on what's on the opposite. So can we reduce the size of it by looking more locally? We try to, okay, I'm connecting all these to one neuron and here. So as we do like in this design here, much better. Let's say if I know I have a 200 by 200 image, I want to connect them, but no, I have by 10 by 10, I only have 4 million parameters. So it's still a lot, but it's much less than 2 billion. And the way we do this local connection here is using something called a convolution. Then I'm able to slide the same weights across the images in an efficient manner, and I only have to update the weights that depends on this filter here of convolution. And if you have forgotten what convolution was, we need to go back to the signal processing and times. Let's say you have an impulse here and you have a filter response. This is the weights that we want to talking about here. And I've applied a convolution on that. That means that I'm flipping this, I'm running it slowly over, and I'm doing a summation and a multiplication and summation over every time shift, obviously, when I'm multiplying these two signals. Then I will have a filtered signals like that. And this is the basic building blocks. And this is local. So now I only have these parameters to estimate and the filter, and it applies to the whole data. So there is a convolution. We often talk about correlation. I mean, it's more or less the same thing in these networks. Different here is in convolution, you have a negative sign here, and in correlation, you have a plus sign. But since we are estimating this signal anyway, we often apply correlation in the neural networks, at least the CNNs, because it's more convenient to implement using matrix multiplications. So that is why, I mean, I'm going to estimate the data anyway. So it doesn't matter if you estimate the flipped version of it. So it's the same thing. So it's called convolutional neural networks, but it's actually a correlational neural network. Okay, what is that in images? Let's say we have an image, very small image here, and we have a filter kernel here. And we do this, it works by we multiply these two guys here and they make a summation. Then we have -2. And we do that for all these points in the image here, we will have this output matrix here. So what I've done here, taking the blue one here, for instance, multiply every 99 by 1, 103 by 0, and 101 by -1. Doing all this multiplication and then just doing the summation of that. End up with -12. Okay, but also another thing changes here is that the output size is smaller. So I started with a 5 by 5 and I ended up with a 3 by 3. And that is because how should I deal with the borders here? So this is something we need to think of when we're designing these neural networks. And also there's a parameter called stride, and that means how much am I moving this for each time I'm doing this multiplication and summation. So here's a stride 1, I'm moving one place. I could move it 2, but then it will also change. We'll have an even smaller, I will come back to that, output matrix. So we have now, can you compute that? That's quite given. So bigger filtering, the smaller that will be. That's it will be. In order to maintain the size, we often use something called padding. That meaning we're adding zeros across the input image. So I can add a lot of zeros circling the data and apply the kernel here. I will have a new output here. And two things happen. Well, the output size is bigger. Good, we achieved that. But we also see that we have some artifacts here. So because of these zeros, we can have huge numbers. So that's also something we need to be aware of. And yeah, and the output size changes now because we have how many paddings, layer of paddings we're doing, so we can have bigger input output here. Mentioned something about the stride. If I'm jumping 2 steps instead of 1, the output matrix reduces the computer size. So this is something we always think about when we're designing this network, is how much padding, how much strides, and sizes, and all these things. Okay, so what does this convolution measure actually for correlation? It's the question. It's a fundamental question. So I'm not going to ask you questions, but I will just tell you. Some kind of degree of similarity between the image and the kernel. What is measured? So if you have like these kernels here, what are we measuring? What could be similar to something like that? This what we have here. First thing here, so you have a vertical structure. So if I apply this kernel here, I would be looking for vertical structure in the image. I will enhance that. They will be having a big number. Everything that is going orthogonal to that will have a low number. Opposite for this one here, I'm looking for horizontal structure. And here I'm looking for something like a corner. So I'm saying something that looks like this. That's high number. So if you apply like this matrix kernel here on that image, you see all the trees get high structures. And if you have a branch that is like this one here, it doesn't have a high value. This is the way it works. And these neural networks, they're gonna learn all the filters that you apply. And it's not just one. All the coefficients in all the filters in all the layers are going to be learned end to end. So that's the goal. And we're not working with one filter, but we have a multiple filter. So at each, we apply several filters at each stage. And I will want to learn all of them. So what we do here, we take this input and I want to learn a lot of filters. And I'm concatenating at the end, the output. So if I say I have D2 kernels here, I will have an input image with have D2 channels, the output. Instead of 3, like in RGB, we can have many as we want. In a hyperspectral image or whatever, it could be hundreds. I want to learn those, and I will have multiple filters at each stage. And also, when we apply the nonlinear function, of course. Yeah. And there's another layer called pooling layer that is often talked about, and that is just some way of aggregating information locally. It could be the maximum pooling. Let's say we take all these 4x4 here and take the maximum. Then I have the stride there, so I'm using a 2x2 pooling with that 2 stride, and then we end up with this image here. And the purpose of that is to reduce the dimensionality because it can get big. And the other is to get less sensitive to the exact pixel location. So if the object is changing a little bit, okay, it isn't good if it's tuned to be at the algorithm is tuned to be at the exact location. So making this maximum, and I'm doing that in a hierarchical manner, I'm having a more translation invariant recognition system. So there are two most popular is maximum and average. So you can use whatever you want actually, as long as, but these are the most fundamental one. Okay, so moving to a convolutional neural network, that is just a lot of these filters connected to each other in string, so to speak. Start with an input image here. We do a lot of convolutional filtering, convolutions, a lot of them, the D2 filters. We have a new image here. Let's say we do some maximum pooling, we reduce the size of that. Okay, we apply new filters. And you have, let's say, D3 of these, and we have a bigger one here. Okay, we do a new max pooling here. Okay, then we reduce the size. And we have a new filter, a D4 of these filters, larger and larger, and also larger and larger. Not that, doesn't have to be, but that's the case. So this is the CNN. Just, and of course, you have this nonlinear activation function at this layer as well. So if you look at this, let's say here we have 16 5x3 filters. That gives me 1,216 parameters. In this layer here, we have 32 3x3x16 filters. And that gives me some parameters. And then we have another filter, 64 of these, with that one here. What's interesting to see in this design here, I mean, that is a number of parameters are not directly dependent on the input image size. It's a useful feature. Of course, if you change the size here, the size of this will change as well. So that's another thing we need to deal with. But this is what it's good. Okay, jumping back to the first slide here, this trainable hierarchical multi-stage network, deep learning network. We have all these levels here. So each of these may be regarded as a convolution, nonlinearity, or pooling. You can also reverse this, of course. Yes, and it's not only 3 of them, it could be 100. So there's no limit there. Okay, some popular networks that came early. This was from '98, one of the first one that worked on 32x32 images, a very small one, just reading digital numbers. And that has a small network here, not many parameters, 60,000. It's called the Net5. Yeah, and also you have some fully connected layers here. So here we have the problem, okay, changing the input size will make us some problems here, because now we are going from these convolutional layers to something fully connected, meaning connecting all the dots, like in the first design we did. So here we need to think about what happens if I change the size. That will break down here. So, and the same goes for the next one. It's called AlexNet. This is the reason for this deep learning revolution came in place. I mean, back in 2012, there was a group from Toronto that proposed this to solve that in an ImageNet competition, and they beat everyone by huge margin, and everyone jumped into this to look at what they were doing. That was a much bigger network, but it was inspired by this Net5. But much bigger, many more filters, bigger input images, more layers. It used ReLU activation function, not like the sigmoidal that this Net did, and we used GPUs, graphic cards, to do the training. And it had 60 million parameters, a lot, it's much, much bigger. But this really made the breakthrough in understanding images. Okay, one that came a few years later is called ResNet, and that has a new design. I'm not going so much into the details, but it has this skip connection going from the input to the output, and then you do some summation here. So instead of learning what it should be, trying to learn the residual instead of learning the response, and that could be some beneficial sometimes. But I think there are, some of the benefits is that you connect that to a network, and then we have a lot of skip connections going on from the input to the output. And when these came, they were very, very deep nets. Suddenly, we changed to 7 layers to 100 layers. Totally crazy in terms of what we used to be able to do. This skip connection allows you actually to take the activation from one layer and feed it to the end of it. more or less instant. And even more importantly, it also allows the backpropagation to propagate the gradients from the output back to the input in much fewer steps, which is very beneficial because then it was much less sensitive to something called vanishing gradient, meaning that it just died out, it didn't change anymore, or exploding it, everything went totally wrong. So that was a really, really good invention. And still today, this is more or less state of the art. I think it came in 2015 in that area. So there's been variants of it, but this is working. One thing that we should notice is within networks that we start with an image, and typically an image has a few channels. RGB often work with, could be more at least in this context in visual intelligence, where we have other modalities working in place, but normally very few, but a lot of spatial dimensions. So you have like could be 250 by 250 pixels, 3 channels. What this network is doing, if you're looking at it, they're changing that whole the way we are encoding information from spatial. We have much more channels, could be like 4,000 channels in the last layers, but a very, very few pixels. You're recoding it, taking information that was in the image, trying to putting it to something like this. And if you're able to do that, we have a lot of techniques working. I mean, then this classification is simple. We have a lot of methodology working that could be useful for classifying vectors. So this is just a broad overview. Okay, there's something called one-by-one convolution that is also very useful. Normally, if you take a convolution with a number, we're just multiplying it. But here I'm doing a one-by-one by, let's say, 32. And that means taking the inner product across the channels. So I have a response here. So of course I can have a lot of filters one by one. So let's say, and we can use that to reduce the dimensionality, for instance, to go from something 28 by 28 to 192 to something 32. And you can do that. It's very helpful. But it also very beneficial because now we can look at this operation we have here. We're going from, I said that were problematic, going to a fully connected layer. I can change that to 2 convolutional layers instead, doing the same thing. And why is that useful? Well, now I can design a fully convolutional neural network instead of having this fully connected layers in the end. And the only thing that changes now is, of course, if I change the input dimensionality here, the output also will change. But let's say if this is a building block, I mean, doing this trick here for doing segmentation, because then I just want to do a mapping up to the image that I have. And then I'm using fully convolutional networks all the way, no fully connected. So yeah, this is the architecture of a UNet, which is, I will say, the most popular segmentation network. Okay, any questions so far? This was a very, very rapid and brief introduction to CNNs. Now I'm going back into how can we train this? Good, crystal clear. Yeah, if you have questions, you can talk to me later, or any of the postdocs or PhD students. They will be perfectly suited to answer your questions about this. Okay, how can we train these networks? There are some things, and that means we're going to figure out, okay, how can we set up this to do this in terms of learning rate and all these things that we have going on. So first, we need to initialize the weights. It used to be a much bigger issue. Today, I think it's more or less solved in the framework that we are using. I mean, you have a good initialization, you don't think much about it. But you should avoid like 0 initialization. It doesn't work. So then the response will be the same, and it's a bad design. So there's a random weight initialization, and that happens every time. Of course, you can set a seed, but when you do that, also the output, I mean, when you're done training it, will be a new network every time. So you need to think about that as well. So, it's a little bit complicated because you're scaling the variance of your random numbers in terms of which layer you are, basically. Yeah, but normally we don't think about that. Another more important issue is to normalize the data in some sense. I mean, standardize it, normalize it. And typically you have like an input data like here, you can subtract the mean. So we have zero mean and can have a scale with the variance. So it has a unit variance. That's a good design to start with. You can do that for images. You can do that for, okay, we can scale it in between 0 and 1. That will also work. So, but having a way that they are consistent, in particular, if you're using data with different cameras or different equipment, it changes totally. And if you look at the seismic data, you have a huge variance. You have this server, you have this kind of range in numbers. So you got another one, it's a totally different. So you need to deal with that. Otherwise, it doesn't work. And why? What is that helping? Well, let's say if you're starting with some unnormalized and you're trying to do the gradient, it could depends. One dimension could be very squeezed, the other could have or not that, and then you're doing it to try to jump back and forth. And if you do this normalization, the learning is smoother. So because it doesn't have applying one learning rate works in all dimensionalities. Yeah, so that's the reason. So another one is fitting the data, the model to the data. And here is this problem of you're underfitting, meaning we have a too simple model. So let's say we want to classify the circles from the crosses. Making a line here, we do some work, but we do a lot of errors here. These are misclassified, that one, and all these things. So, and going the other way, we can try to encapsulate a very complicated surface here, learn that, and it will work very fine on this exact data set. But what happens when I get new data? So that's a problem. So maybe this one is the best one to strive for. In terms of, so what we do then to do that is we try to prevent this. So if you have overfitting, what can we do? Well, you can get more data to do design. Or you can try to add some regularization. I will come a little bit back to it later. In order to avoid this high variance. You can also look at the learning curve. So if you're training it, it's improving all the time. The loss is decreasing, but if you evaluate the loss on the validation data, which I say you are using during training to figure out how good it's working, you suddenly at the one point start to increase. And that is when you're overfitting. So monitoring this is crucial. Well, underfitting then is the opposite. So we are on this side, we haven't trained it too long, or it's not big enough. So that is an easier thing, because what you do is just to add more layers of neurons in the network, and at one point you will have so much that it starts to overfit. You could reduce the amount of regularization if you have that included. Okay, I mentioned regularization a few times. It goes back actually to regression. I mean, you do regularization there, then you penalize large weight. Ridge regression is one example of that. Remember that from statistics. By adding another term here, okay, saying, okay, if the weights are large, you get penalized. So you can use the same in the networks, meaning that you will put if some weights are very high, other must be very small. So meaning you have effectively fewer weights going on. Dropout is another that is very popular, meaning that during training, I'm randomly dropping some weights. For instance, this one here. Okay, setting, okay, I'm not using these neurons anymore. Try to learn a network without this. And the next iteration, I'm dropping someone else, and so on. So you are going through this for each time your iteration, you're dropping new weights. And that's a good thing. It helps define a reduced network, basically. And it helps you the network to be less prone to overfitting. So the idea is that, okay, you cannot rely on any feature inside this network, so you have to spread out all across the way. Try to learn a good way of avoiding that some weights are, the performance is highly dependent on a few weights in the network. Or test time, you don't do it normally, but you can do it. And if you want to do some uncertainty estimate, that's a way of doing it. But yeah, you normally don't do it. Data augmentation is another trick that we use when you train a network. And also is to prevent overfitting. Have more representation of your data into the network. And this is something that I always do. So particularly if you have a limit data set, but I do it anyway, more or less. And what you typically do is a kind of grid transformation. You're flipping the data. So let's say if you have this cat, you can flip it, look like it. It's still a cat, you see it. So this is a very, very efficient way of doing it. You can do some translation, maybe you can crop it, you can rotate it slightly. Okay, you rotate it, you may have some edge effects in the image, but it's possible. You can add noise. You can blur it, you can do some contrast adjustment, lightness adjustment, a lot of things you can try to do. And you do that. It depends, of course, if you look at object recognition, these could be adding noise could be a good thing. But if you're doing remote sensing and you have a very highly sensitive to spectral values you measure, maybe that's not the smartest thing to do. Change everything. So yeah, so you need to think about that as well. Early stopping is something we are, like I said, we're monitoring this curve. You can choose this one where you have the validation error was smallest. So or stop the training. So if you don't want to spend time on that. Another thing, batch normalization is something that was popular. You do that normally. And that means for each layer, you're normalizing the response by subtracting the mean, dividing by the variance. You also introduce a couple of parameters that you are learning in order to do that. Yeah, this works. It also acts like a regularization. There are a lot of ways of interpreting this, smoothing the loss curve and all these things. But this is a useful thing to do, and it all often give you better results. So batch norm layers is very often included. In test time, you're using some pre-computed values of these parameters. So they are estimated during the training. Okay, but if you use batch norm, there's no need for this bias term in the convolutional layer because they are canceling out anyway. Okay, so this is first like standard. You do that in order to help the training networks. Something called hyperparameters, and that means all parameters that are not weights biases in the network that you use to train this. So, and they are crucial because they are the one you are tweaking with in order to train the network. So there are many hyperparameters to tune. It's the first thing. A lot of them. They're not orthogonal, and by that I mean if you look at the TV, I can change the sound and the channel by 2 different knobs. But think of a TV that you need to, if you're going to have a higher volume, you need to change both simultaneously in some strange manner. And that is what happened with the hyperparameters. If you change one, the other one else, it's not like you can easily go to tune one and then the next one. This is a complicated thing. So the learning rate, the most important thing. Not too big, then it jumps back and forth. If it's too small, it's going too slow. So this is emphasis with this curve here. So yeah, low learning rate, slow convergence, very high, explodes. Good learning rate is the red one. This is where you want to be. Yeah, weight decay, meaning that how much should you weight is L2 loss function is also a little bit important. We do something called learning rate decay. After we're training, we are decreasing the learning rate. It helps. So if you're close to an optimal, you don't want to have a very high learning rate because then it jumps out of your minimum. So you want to do that. And there's something called momentum, which is actually exponential decaying average gradient estimate. So instead of using the gradient, you're using an average of that. They're also helpful. But then you introduce a new parameter beta. Okay, you need to figure that out as well. And there are a lot of more complicated versions of this called ADAM or ADAGRAD. There's a bunch of things you could do. I will not talk about that here. In addition, you have the number of layers, number of filters, and filter kernel size. You also need to set. Okay, evaluation. I will not recommend grid search like this. Use a random search instead. And the reason for that is simple. It's difficult to know in advance which one is important. So here, if the hyperparameter 2 is not important, then I only get 5 elevations of 1. But if in this case here, I get all of 20. So better design. So here's a table just summarizing, okay, where to start. So if you learning rate, typically between 0.001 to 0.001. Start there, try it. And 0.9 is a very typical term for the momentum. Rate decay, you have to start with 0. And then you can add these parameters. So I'm going to add them. I didn't talk about that now, but this is a set. Mini batch size, I didn't talk about that, but then there's another parameters. Typically, it depends on the memory of the GPU as well. And this dropout probability, 0.5, start with that, and you can tune it later. Okay, so what should you do here? Reducing the bias and variance. So I think we have three ways of looking at it. You have the human level error rate, you have the error rate during the training set, and you have an error rate during the validation set. And if this is high, how can we reduce that? Well, you can train bigger models. Or you can train longer or better optimization algorithms. You can try another neural network architecture, or you can try to do some hyperparameter search in order to make this as small as possible. The other one is more harder to solve. So if you validation error rate is much higher than it's always higher, but it's much higher, and then we have some issues here. So try to figure out what are the errors. Are there something in the data? Something, why is it going wrong? Try to just figure that out, and maybe get some more data. That will also help. Do some regularization could be beneficial, and try out the networks and hyperparameter search. So this is the one that you most likely will end up with having issues with. Okay, and that's mostly related to have too little data. Okay, an interesting thought. When I was a student back in the 90s, we had this textbook, Convolutional Neural Networks by Simon Hakin. 800 pages thick Bible that we were reading. 2 pages on convolutional neural networks. So that was the Net 5 architecture describing that. Okay, basically done with the first part. The next part is why AI fails. I don't know if I have time for that. It will take more than 2 minutes, so I need to steal some more time then. Could be the most interesting thing for and that is why it goes wrong. So the first thing is the quality of the annotations. So let's say here's an example. We are using roads, want to segment roads, and you have this something that this is missing. Here we're doing a shortcut. All these things, low precision, incomplete, all these things degrades the performance. Brittleness. So this is something we will discover. It is easily fooled if you are having a new patterning. Let's say this is an example. You're changing the view of the bus, and suddenly it goes from a school bus to a snowplow. We all see this is not a snowplow, and this is a lot of cases you can do this. So it's not capable normally of doing this task of mental orientation that we are. Can add something on the stop sign, it changes. Dangerous. So you need to think of that. That's why brittleness. So it's important. Or you have new data. Let's say we have working on this land cover mapping here and a few nice summer data, and then we are a little slightly into the fall. Everything breaks down. It's sand all over Hardangervidda. It's not what we wanted. So the brittleness. So to solve this particular data set shift, it's no golden solution for it. It's not okay, we do that, fixed now. So you need to understand the problem, collect more data again, covering a variety of things, do data augmentation. Maybe some domain adaptation strategies could work, but still that could be dangerous as well. Semi-supervised learning, adding a few labeled pixels from the test data could also be. Another issue, embedded bias phase AI. So we have a sample bias. Okay, we have not enough training data, doesn't replicate the real world. We can have some kind of bias related to that, social status, gender, race, things. Algorithmical bias. It's not the appropriate algorithm we're using, or it could be data excluded from the training data set. That could be important. So it's a typical case here. We are looking at cooking, and it wanted to be a woman. Even a man is cooking. So you have this bias with gender. Class imbalance is another thing that we often expose yourself. Related to that, a lot of more samples from one class come to the other. So it's very difficult to make this machine learning algorithm to understand that. You can try to weight them, you can do some smart sampling scheme, add them, remove data. But it's not easy, and you should not use accuracy. Precision recall is better. I mean, that can also have some challenges. Another thing is something called catastrophic forgetting. It didn't work much with that, but if you learn it one task and try to do it for another task, learning it, it forgets what it has learned previously because all the ways will be changed, and so it doesn't work anymore. Explainability, important. We are addressing that here as well. So why do we have these predictions here? So this data is back to this clever horse Hans, which were able to understand the man here, the sub what he was pointing at. Not the case. I was good at reading him, but not the letters. Yeah, you have this classical thing where you're trying to recognize huskies from wolves, and it turns out to be snow in all husky wolf images, and that's what the network was capturing. Uncertainty is another issue. Okay, we need to have a way of they could be very certain. That's the problem. They're so certain. Okay, I'm giving a high score value. What's wrong? And it doesn't reflect that. Here's an example from Christopher's publication back where he was using uncertainty in order to enhance his predictions. And most importantly is the total lack of common sense. They are damn stupid, mildly. Now, it is not able to reach acceptable, logical, conclusive based on a vast context like knowledge that you have and human are able to do. It can learn shortcuts and lead them to misbehave. Here's one example. We were trying to map these roads, and it did very well on these IOU metrics that we use, but it was not able to understand that the roads should be connected. We don't have a 10-meter road in the middle of the forest. But the score values was great. I mean, what we were measuring. But okay, why? What's happening here? Yes, finally, conclusions. Yeah, deep learning, it was people were solving problems we cannot do 10 years ago, definitely. But data is the most important thing. That's what's driving this. A lot of challenging left. All the AI fails examples, this is what we are addressing here at Divisional Intelligence. Exactly. All the points there. You can find them what we in the research plan, what we're trying to solve. Okay, that's it. I have one more slide.